is pretty big for a couple of reasons. Myeloperoxidase at the blue-green tint, they'll show you a picture or they'll say, hey, it doesn't turn blue, what's missing? Bam. Pyocyanin, Pseudomonas aeruginosa, they love that, and lactoferrin, they also like this. They're like asking you questions about chronic granulomatous disease and about everything kind of in this pathway, because it's so easy to test something, to just put an arrow and say what's missing, put an arrow and say what's missing, put an arrow in here and say, hey, what are they going to get infected by? Staph. Well, they'll do something like, is it going to be a gram positive or a gram negative, whatever. You know, they can test that in so many ways. So this is super high yield. You know, one of the ways that this causes an issue is that, of course, if you know your job is to create radicals, or if your job is to create these reactive oxygen species as one of the mechanisms to kill things, not just bleach or whatever. Well, if you knock out one of those, then you make it easier for the other remaining bacteria to survive. So that's why things with catalase are particularly adept at affecting people who don't have this, because, well, they can kind of, you know, go away from this problem here. And so, you know, this is ineffective and this is ineffective, and so the bacteria can obviously thrive. Okay, the next thing is this right here. Here we have glutathione. Glutathione is either oxidized or glutathione is reduced. Now, this whole little sequence can sometimes be difficult to understand, but if you think about it just in terms of how electrons give energy, it makes it a lot simpler. Think about any bond in your organic chemistry class and what happens when you just blast it with energy. The bond gets broken, or it goes from a double bond to a single bond or something. So the same thing happens in real life. If you're holding someone's hand and someone comes in and karate chops it, you know, gives a bunch of energy and really breaks that connection. So it does the same thing here. Glutathione is oxidized. Okay. Let's start from the top. Here you have a reduced form. Of course, reduced means that it has an electron to spare, and it goes and it breaks this peroxide to H2O. Okay, so now this is missing an electron. Fortunately, NADPH has an electron to give with its hydrogen. Okay, so it gives its electron to the oxidized glutathione, which is here turns into reduced glutathione. But our NADPH is now missing an electron. So what happens? Well, fortunately, our glucose 6-phosphate ends up giving an electron here. Same thing. So the idea is that we can go from the top down, or from the bottom up. Let's go from the bottom up. Boom, gives an electron. Okay, so this thing here is losing one electron, or has one electron less than its glucose 6-phosphate. Okay, but that electron went here to NADPH. This NADPH is going to give its electron to the oxidized glutathione, which is now reduced, which is now going to break down H2O2. And interferons. The biggest application for interferons really has to do with HPV. Especially when you take step 2, there'll be a lot of different questions about, like, when do you give interferons for, like, what different, like, types of hepatitis and stuff. But the biggest thing here is just to understand how it messes up with RNA anti-antiviruses, and so it's applicable throughout a huge spectrum of pathologies. Okay. And there are, of course, gigantic adverse effects. Neutropenia is huge. And flu-like symptoms is a very mild way of putting it. So hopefully in this page you kind of understood how the movement of electrons, either from the bottom up or from the top down, affects kind of your response to bacteria and how everything gets killed. and of course not just how things get killed, but also how you're able to turn things like peroxide into friendly just water. Because if you couldn't, that'd be kind of bad.